In this part of chapter 12, I would like to explain the topic of risk when applied to stock investment. On this figure, we have several lines going up. So imagine your great-great-great-great-grandfather or some distant relative invested $1 in 1925. And let's say that relative of yours had 3 more friends. So the 4 of them each invested $1. One bought however many shares of stock he could with $1 of a small company, different small companies. That's the green line. And so when $1 was invested in 1925, it was more or less increasing in value over time as prices of shares of stock of small companies in that portfolio that was purchased were going up over time. The second person also invested $1, but instead into shares of stock of large companies. That's the orange line, a little bit below the green one. And then the other 2 invested in bonds. One bought government bonds that make payments over a long term, the blue line, and the other one, the brown line, the one that's below the other 3, is treasury bills. Also government bonds, but short-term government bonds that pay the money back over several months. And let's ignore the purple inflation line. So just focus on the first 4, the top 4, green, orange, light blue, and brown. So we are comparing these 4 historical investments, how the money has been changing when invested into each of these investments individually since 1925 until roughly 2013. 2013 is the last year. So this 88-year time period. And in the earlier slides, in this chapter, we saw how the fact that the small company stock line, the green line, is the steepest. It implies the highest return that was earned on average every year. The second highest average annual return was for the orange line, the large company stocks, and so on. Now we want to focus on risk. Which of these 4 investments that we are considering has been by far the riskiest? The best way to look at it is to look at the jumps. What do the jumps mean? Sometimes you make a lot of money, then you lose a lot, right? Which one of these 4 lines is the jumpiest? Which one has the most up and down changes along this trend? It's kind of obvious that the green line is the winner, or maybe I should say the loser, right? Because when we talk about risk, we mean something bad, right? So it has been experiencing the most fluctuations or volatility or variability. So volatility, variability, risk, uncertainty about what you get every year, it all means the same thing. So the green line, small company stocks investment, has been by far the riskiest. The second riskiest has been the large company stocks. So stocks in general are the riskiest investment, or at least have proved to be the riskiest historically. And bonds, government bonds, are safer, lower risk, more certainty about how your money will be growing. In other words, what return you will be receiving every year. So not as jumpy, not as volatile. From the bonds, the government bonds, the shortest term, the treasury bills, the brown line, is the safest one. So this is what we are seeing when we just look at the historical data, at the returns that are already known to us for these different investments. And this is how these different investments compare to each other. So How would we calculate risk? How would we measure the amount of risk in different stock investments? Let's forget about stocks and imagine we are, somewhere fun like Las Vegas. Imagine there are two slot machines. You can play slot machine number 1 or you can play slot machine number 2. We are going to answer the question, which of the two machines is better? Let's say if you play machine number 1, these are the 4 possible outcomes, and they're equally likely. They're kind of randomly repeated, right? Over and over and over and over as you play the machine. You can win $100,000 or $75,010 or $25,010, or you can lose $200,000. If you instead play machine number 2, you can either win $100 or win $30 or lose $5 or lose $105. So these are the 4 possible outcomes for the two machines, and they are randomly repeating, so we can say they are equally likely, right? So let's say, you've been playing these two machines, first one, then the other. Which one has shown the more risk? Which one has been riskier? Which one has been safer? First, if you do the right math, you would realize that it doesn't matter which machine you play if your only goal is making money. You actually end up with the same amount of money on average. How do we know that? Well, add the 4 possible numbers up and divide them by 4. That's your average gain per game as you play it over and over and over. $5 if you play slot machine number 1. If you do the same math, slot machine number 2, so you add up 100, 30, -5, -105, and divide that sum by 4, you get also $5. So it looks like it doesn't matter which machine you play if your own comparison is how much you make on average per game. But what about the risk? Are the two machines similar in how risky they are, how much risk they offer, how much uncertainty they offer to you? Well, you don't need to do the math to realize that machine number 1 is riskier, because the numbers are so much apart, so far apart. You can win up to 100K, but you can lose 200K in one shot. Whereas slot machine number 2 is better because the 4 numbers are not that far apart. Apart from what? From the average. And that's how we measure the amount of risk. We want to calculate something that tells us how far on average from the average we would be if we play each machine. This is exactly what the concept of the standard deviation does. So usually we calculate the variance first and then the standard deviation, but both tell us exactly the same information about the amount of risk. So in other words, we want to calculate how far on average our 4 winnings separately for each slot machine are away from the $5 average that we have just calculated. Let's look at machine number 1. We calculate the distance from $5 for each of the possible outcome. So 100,000 minus 5. And we want to add up those distances from the $5 average and, find their average, the average distance from the $5 average. But if we don't add the power 2, we're going to get 0, because everything will cancel out. When we win, we may be above the $5 average. When we lose, we will be below. And that's why the sum of all distances will always cancel out perfectly, and we would get 0. In order to not get 0, we can use this trick by adding the second power, squaring the distances from the average. and that eliminates the whole, plus sign being cancelled out by the minus sign for some of the terms. Another little detail that's important when we look at historical variance calculation, we don't divide by 4, but we divide by 4 minus 1. This is something they call the degree of freedom in statistics. So the stat field is sort of where you would learn kind of the depth of this way of calculating the variance more accurately. So not by 4, but by 4 minus 1, which is 3, in other words. So we get this large number, that's the variance, and then we take the square root of that, which is in a way removing that second power that we added, just so nothing gets cancelled out. So the square root of variance is the standard deviation, and we get $136,933. This means that if we keep playing the slot machine number 1, we would be on average earning $5 per game, but the actual amounts of money we would be making or losing would be $136,933, either above or below the $5 average. So that's the average distance from the average. We can now do the same calculation for slot machine number 2. Squared deviations from the mean added up divided by 3. So not by 4, but 4 minus 1, which is 3. That's the variance. The square root of that is the standard deviation, $85, which means we are winning on average $5, but the actual amounts we would be seeing are on average $85 above or below $5. So again, it's the average distance in either direction from the mean. This is how the standard deviation actually calculates the amount of risk. And so now we can compare the two machines sort of in the scientific way. We calculated the standard deviations. Which one is higher? Slot machine number 1. That's the riskier machine. This is how we compare risk. And it's definitely more relevant when we are not sure by simply looking at the numbers which one implies a higher distance from the average. In this example, it's pretty obvious, but when it's not, you have to calculate the standard deviation, which will tell you exactly where you see a higher amount of risk. Okay, now we apply exactly the same formula to what we are learning in this chapter: stocks and bonds, actually, financial securities. So variance and standard deviation, that's how we actually measure or calculate the amount of volatility, or how much change we see in the returns of our assets, stocks and bonds. And the higher the jumps, the higher the uncertainty regarding what you will get every year, and that would result in a higher variance and standard deviation. So more jumps, higher amount of risk. Okay, so historical variance, we calculate the squared deviation from the average, then we add all of them up and divide by how many we have added up minus 1, which is this general formula: variance, or VAR, of returns. Sigma squared is a common symbol for it, and again, R's are the returns. So R1 means return in year 1. In our particular example, that's the return going from year 1925 to year 1926. R2 is going from 1926 investment value to 1927 investment value. We calculate the return in percent. That's R2. RT, in our case, that's for going from 2012 to 2013, our last 88th year in our historical time period. And R bar everywhere is the same number. That's the average return, just the simple average for that entire 88-year time period. Once you find the variance, you then take the square root of that, and that gives the standard deviation, which tells you how many percent above or below the historical average return you were on average in each year.